All right, welcome to a fairly quick video over the basic probability rules. There's a couple basic probability rules that all kind of blend together, but you need to know and understand how they use. Let's start off with the multiplication rule. This is a very, very famous rule that a lot of kids actually misuse. All right, the multiplication rule says that the probability of A and B, that upside down U is our math symbol for and, the probability of A and B is equal to the probability of A times the probability of B on the condition of A. And that's what actually a lot of kids forget. They think that the probability of A and B is just A times B. Well, you're going to learn that video that this is wrong. It's the probability of A times the probability on the condition of A, right? You have to constantly be thinking, does what I do second change because of what happened before it? So this introduces us to the conditional probability rule. When you see that line, we're talking about conditional probability where something is known or given. So again, if I'm taking the probability of A and B, I start the probability of A and I multiply by the probability of B. But remember, A has already occurred, so that's why I have to have B on the condition of A. So the conditional formula is equal to the probability of A and B on top divided by the probability of B. Now this is what's crazy, right? If you just think about this for a second. If I take the formula for conditional probability and I substitute it in here, you basically get a formula for the probability of A and B, but to solve that formula, you need the probability of A and B, right? And let me kind of explain this to you one more time, right? So if I'm just going to substitute, so I got the probability of A multiplied by, well, the probability of B on the condition of A is the probability of A and B divided by the probability of the condition A. Now, I want you to understand here, I flipped these, right? And it doesn't matter. I could call them smiley face and lightning bolt or C and D. It doesn't matter. But according to the formula, whatever the condition is, that goes in the denominator. So what I'm working right here is the condition is the A, and that's why it goes to the denominator. The top is always A and B. So what happens is these probabilities of A's actually cancel out, and you get the probability of A and B equals the probability of A and B. So it's like, great, where'd that get us? And that is why a lot of kids actually use this rule wrong and then don't understand why their answer is incorrect. So what we have to understand is that basically if you're using the multiplication rule, right, it's trying to tell you that you have to think. If you're looking for two things to happen, A and B, think about A. But then when you go to think about B, you got to consider the fact that A has already occurred. And there's really no way to, understand this other than just being able to comprehend what the rule means. And that's how you use it. So with a two-way table, this is actually pretty simple. So if I look at this two-way table here, we got, do you work on the day shift or do you work on the night shift? And do you take a break or do you not take a break? All right, two-way table for two variables. If I ask for the probability that somebody works on the day shift and, there's our upside down U that stands for and, probability somebody works on the day shift and takes a break. Well, I hope you understand one thing. When you have a two-way table, this number is literally in the table. It is right here, 31 people. That's your answer. 31 out of the 215 people. That's the answer. You don't have to do any work. That's the answer. There's the overlap between the people that work on the day shift and the people that take breaks. Boom, there it is. But the formula does work, and that's what a lot of kids don't realize. If I want to actually use the formula, literally use the formula, I need to take the probability of working the day shift, and I need to multiply it by the probability of taking a break on the condition that you work in the day shift, right? Because that's what the formula says. And a lot of people kind of forget about this back part. They just do day shift times break. And again, they wonder why their answer is not right. So if I'm going to do this, let me walk through it and show you. The probability that you are on the day shift is, well, day shift, there's 129 workers out of 215 workers. Okay, so got that part down. Put it in parentheses. And then now I got to multiply it by the probability that you take a break given you're on the day shift. Well, that's a formula itself. The formula for conditional probability, let me kind of come to the side here. The formula for conditional probability is the probability that you take a break and you're on the day shift divided by the probability that you're on the day shift. Now at this point you might be like, wait a minute, I'm trying to find the probability I work the day shift, and take a break. How am I supposed to find that probability using the formula if I need that probability? Well, exactly. That's what I'm trying to teach you. Look in the chart. Day shift and break is 31 people. So the and is 31 out of 215. That's the numerator. Divided by the denominator is the probability that you're on the day shift, which is 129 out of 215. Okay, so here is the back part. Here is the probability that you take a break given you're on the day shift, right? On top is and, 31 out of 215. On the bottom is day shift, 129 out of 215. Well, if you understand mathematics, you should be looking at this and realizing, wait a minute, the 129 out of 215 right here cancels with the 129 out of 215 right here, and I get an answer of 31 out of 215, which is true. So the whole point is like, I didn't need that formula. I just needed to look at the table and see that 31 people both are on the day shift and take a break out of 215, and I get the answer. It's that easy. Don't overthink it. All right, let's look at another rule called the addition rule. All right, the addition rule involves the probability of A or B. This normal U-looking thing actually stands for union. That's or. All right, the formula for or is the probability of A plus the probability of B minus the probability of A and B. And what you have to do is you got to subtract the and. You got to understand this. I'm not getting rid of the and. I'm just getting rid of it from being double counted. A Venn diagram is a nice way of showing this. If I have my sample space here, and I take the probability of A, so there's the circle for A, and there's the circle for B, the probability of B. If I want to find A or B, well, then I'm going to add the entire A circle, plus, let me grab a different color here, plus the entire B circle. Well, there's A, there's B, but if you think about it, this part in the center right here got counted because it was a part of A. It got counted because it was a part of B. I want that part to count, but not twice. That's why we subtract away A and B. So it's a pretty useful formula. In fact, I'm not trying to discredit the multiplication rule. It's a great formula. But this formula is really important because this formula involves A or B. It involves A, it involves B, and it also involves A and B. So what a great formula, right? So anytime, and I repeat this as many times as I can, obviously you just rewind it and hear it multiple times if you want. But the idea is that if you are given an OR probability, or you're asked to find an OR probability, use this formula. My goodness, don't consider doing anything else. And let's actually look at an example of what I'm talking about here. All right, so here is back to our table. Day shift, night shift, take a break, not take a break. What if I said, what's the probability you are working the day shift or you take a break? Okay, well, I'm going to follow the formula. I'm going to take the probability that you take a day, that you work the day shift. Probability you work the day shift is 129 out of 215. And I'm going to add the probability to take a break. 64 people take a break out of 215. But if you think about that, what I did was I took the day take a break column. I took the day shift column. But what happened was 31 people got double counted. 31 people got counted because they were on the day shift. 31 people got counted because they take a break. But those 31 people got counted twice. So that's the overlap. I mean, literally look at the two like circles I made. That's the overlap. So I'm going to subtract the 31 out of 215. I'm not getting rid of those people. I'm just preventing them from being counted twice. So I already got a common denominator, so just add my numerators, 129 plus 64, subtract the 31, and I get 162 out of 215. So very, very easy. And quite, it's actually, very simple. So pretty easy formula to really, really use and take advantage that it could actually help you a lot. All right, let's look at another problem here that obviously, kind of gives kids a lot of fits. All right, in a certain area, it is known that 28% of people exercise daily. Great, awesome. And 38% of people eat fast food daily. Okay, great. It is also known that 55% of people exercise daily or eat fast food daily. All right, now I could ask you a whole bunch of questions with this, but one question that you're probably going to see is, hey, what's the probability that you exercise daily? And there's that upside down U that means and you eat fast food daily. All right, what most kids are going to do is they're just going to jump and they're going to take 28%, they're going to times it by 38%. 0.28 times 0.38. You're wrong. Remember, the formula is the probability that you exercise. Okay, great, we do know that. Times the probability that you eat fast food on the condition that you exercise. That's the multiplication rule. Well, okay, I know the probability you exercise. That's awesome. Okay, I know that, 0.28. Okay, but to follow the conditional formula, now I got to think about the fact that in the numerator is the probability of both. I'll put an FF for fast food and exercise, EX, divided by the probability you exercise. Oh, okay, well, once again, all right, I know the probability I exercise 28%. I have no idea what the probability of both is. I mean, in fact, that's what I'm trying to find. And then again, in the denominator, I do know the probability I exercise, 28%. Okay, the 28% is cancel, but I still haven't found the answer. I mean, literally, I'm finding exactly what I'm looking for. So that's where it's like, don't just multiply them, because that's not right. So how do you actually tackle this problem? Well, like I just got done saying, anytime you are given or asked to find an OR probability, you're going to need to use it. So the probability that somebody exercises, I'll put EX, or has fast food equals the probability that you exercise plus the probability that you eat fast food minus the probability that you exercise and eat fast food. Wait a minute. Of the 4 things here, I know 3 of them, which means I could solve. So the probability of exercise or fast food, we know is 55%. Probability you exercise, 28%. Probability that you eat fast food, 38%. Minus, well, I'm going to put a big X right there because I don't know what the probability of exercising and fast food is. That's what I'm looking for, and now I could solve. I'm going to subtract 28%, subtract 38%, and then I do have to divide by a negative to solve for X because there's a negative in front of that X. So 0.55 minus 0.28 minus 0.38 is negative 0.11, but then you got to get rid of that negative, so we get 0.11 equals X. Okay? So there it is. 11% of people exercise and eat fast food daily. Well, that's not extremely low, but it's not surprising that's a little bit lower because if you exercise, you're probably healthy. Why would you eat fast food? But again, 11% of people do both. Now, if this is causing you any kind of angst, here is another way that you could do this problem. You could think about exercising as a yes or no, and then you could think about fast food as a yes or a no, and you're basically going to make a little table here and fill everything in. So we know that 28% of people exercise. Complement rule says 72 do not. We know that 38% eat fast food. Complement rule tells us that 62% do not. Now, this is something also important for you to know. The opposite of or is none. Remember, or means A or B or both. It just doesn't mean none. So if I know 55% of people exercise or eat fast food, then the opposite is the 45% that do neither. No exercise, no fast food. Now, once you know that number, you could just use some very simple math to solve the rest of this chart. So, for example, this column right here adds up to 62%. So this has to be 17%. That way, 17 and 45 add to 62. This row right here adds to 72%. So this number must be 27%. That way the 27 and the 45 add to the 72. And then now I could find this yes, yes, exercise and fast food 2 ways using the row or the column. Regardless, I get the 11% that I knew was the answer going into it. So that's another way that you could solve that problem. But what I'm actually trying to get across in this video is don't multiply. Because the only way you're allowed to multiply is if you know the conditional probability, which I'm trying to teach you, you don't know in this problem. Now, if you do know the conditional probability, well, then you are allowed to multiply. All right, let's take a look at this problem and see how the multiplication rule is going to help us here. A sample of 18 students was selected from a large high school. 4 students will be selected from those 18 without replacement to receive a free pass to sporting events. Let X equal the number of boys selected to get the free pass. All right, first question says, well, let's think about that real quick, sorry. All right, so if X is the number of boys that get a free pass, could be all 4 of them, 3 of them, 2 of them, 1 of them, or none of them. And I can also look at this through the perspective of girls. If 0 boys, then it's 4 girls, 1 boy, 3 girls, 2 boys, 2 girls, 3 boys, 1 girl, 4 boys, no girls. But anyway, the question asks about boys. All right. If the original sample of 18 had 9 boys and 9 girls, what is the probability that all 4 selected students to get the free pass are boys? Now, the problem here is I have to think conditionally, but I'm not going to use the formula. I'm just going to use my brain. I want the probability that all 4 are boys. So let's see here. If I reach in, there are 9 out of 18 boys. But what happens the second time is changing. It's not independent, because what happened on the first selection impacts the second, which means my mind has to think conditionally. Now there's only 8 out of 17 boys. Then I need a third boy. Well, now there's only 7 out of 16 boys. And lastly, I need a fourth boy. There are 6 out of 15 boys. So to get my final answer, I'm going to take 9 times 8 times 7 times 6 in the numerator. And I'm going to divide that by the denominator of 18 times 17 times 16 times 15. And I get 0.0411. 0.0412 actually, sorry, 0.0412. All right, so there's a 4% chance, about a 4% chance, that all 4 kids selected are boys. But the point I'm trying to make is I was able to multiply there because I thought conditionally. That's what the multiplication rule is all about. All right, after the 4 students were selected, it was found that they were all boys. Does this surprise you? Well, let's stop right there. Does this surprise me? Well, the probability of it happening is about 4%. I mean, that's lower, but honestly, personally, nothing really surprises me until it's under 1%. So I don't really think that personally this is that surprising, right? If I kind of hold true to my 1% threshold, this is unlikely. It's on the lower side, but I wouldn't say that this is, oh my God, all 4 boys, this is impossible. I mean, I don't think it's that surprising. So this next question is actually a really good one. What does this result give evidence that the sample, does this result give evidence that the sample of 18 was equally split or not? Now remember, we found this probability on the assumption of 9 boys and 9 girls. So if all 4 boys are selected, does this tell me that my sample was equally split or not? Now, honestly, a lot of people are going to jump and say, oh, no, it wasn't split. If you got all 4 boys, then there must have been something funny going on. But not really. I mean, the point is if we did have an equal split, the probability of getting all 4 boys wasn't that surprising. If it was surprising, well, then maybe I would say it wasn't an equal split. But basically what I'm trying to get across to you guys is that, listen, what happened wasn't really weird. So can I say that there are more boys than girls in this sample of 18? I mean, not really. I mean, listen, at the end of the day, I don't know. I was just assuming it was 9 and 9. Maybe it's 10 and 8. Or maybe it's something a little bit less than that. But the point is just because I got 4 boys doesn't tell me it's not. Like, you know, if a girl wanted to come and say, this isn't fair, all the boys got picked, I would say to that girl, well, I understand that you feel that way, but the probability is 4%. That's possible. So I know you think that it's like maybe I cheated or that the boys were unfair, but listen, it had a 4% chance of happening. It, you know, could have been 4% chance that they were all girls picked. So it's not that weird. So at the end of the day, do I know it's a perfect equal split? Not necessarily, but I don't think that it's not, because this wasn't surprising. Hopefully that makes sense. That's kind of an advanced topic, but I hope it makes a lot of sense to you. All right. Now, the other thing I want you to understand is that the multiplication rule is so powerful, and you could directly use it as long as you are thinking conditionally. So that's what this last question is going to help us do. It's going to really make us think conditionally. All right, studies show that 2% of dogs get heartworm. A new test is used to help diagnose dogs with heartworm. If a dog has heartworm, it will give a positive result 95% of the time. That right there is a conditional statement. If the dog has heartworm. So if I am one of those 2% of dogs, then I have a 95% chance of having a positive test. If a dog does not have heartworm, it will give a negative result 85% of the time. That's another conditional statement. If the dog does not have heartworm, that's the 98% of dogs that don't have heartworm, then 85% of them get a negative result. Now, if you ever have one of these kind of conditional, when you read a question where you see these if statements, a tree diagram really helps. So if here is a little dog, bark, 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 okay, little doggy. Well, first off, understand that there is a 3% chance the dog has heartworm. I'll use an HW, which instantly tells me the complement rule, 97% chance it does not have heartworm. Now, here's the conditional. If it has heartworm, there is a 95% chance of a positive result on the test. Complement rule, 5% chance of a negative result. That would obviously be a bad thing. That's a false negative. That's telling a dog it doesn't have heartworm when it really does. It happens. Now, if the dog does not have heartworm, 97%, then there's an 85% chance of a negative result. Complement rule, 15% of a positive result. Once again, that's a false positive. It's telling a dog that they do have heartworm when they really do not. But again, the point I'm trying to make is that these probabilities were on the condition of what came before them. So the question here says, what's the probability the dog has a positive result? Okay, well, there's two ways you can get a positive result. You could have heartworm and get a positive result. I'm directly allowed to multiply those probabilities because the 95% came from the 3%, right? It's literally the multiplication rule. So the probability that a dog has heartworm is 3%. The probability that you have a positive, given that you had that heartworm, was the 95%. So I'm literally directly using the rule here. But there's another way you could get a positive result as well. You could not have heartworm and still get that positive result. So that'd be 0.97 times 0.15. And again, that is also using the multiplication rule. The probability that you get does not have heartworm, 0.97, times the probability that you have a positive result given that you do not have heartworm, because that's where that 15% came from. So put all that together, we get 0.03 times 0.95 plus 0.97 times 0.15, and we get 0.174. So there's about a 17.4% chance that a positive result pops up for any given dog. All right, now we have, a given. Now we need to use our great conditional rule. All right, given a positive result, what's the probability a dog has heartworm? So we want to find the probability a dog has heartworm given that there's a positive result. Remember, the conditional formula on top goes both heartworm and positive result. Well, once again, we know that, right? That's 0.03 times 0.95. And again, where did that come from? That came from the multiplication rule. I took the probability of heartworm, 0.03, multiplied by the probability of getting a positive result, given that you have heartworm. Well, that's exactly what the 95% was. And then the denominator goes just the condition. So the probability of a positive result, which is already all the work we did. So if I just copy that work down here, that's 0.174. So take the 0.03 times 0.95 and divide that result by 0.174, and you get 0.1638. Okay? So if there is a positive result, there's only about a 16.38% chance that that dog has heart. All right, so I know that was kind of a quick video, but it really comes back to those rules, right? You have to understand the rules. So many kids misuse the rule for multiplication. They just blindly want to do the probability of A times the probability of B. But what I'm trying to make you understand in this video, you got to consider that A has already occurred. So, and then again, which makes this like really kind of hard to comprehend, is that formula for conditional probability needs the and. And that's why the only time you could use this formula is if you understand conditional probability. You understand, you could process, you could think that when I get to that B, I got to think what has already happened to A. Or, like I said in the last example, we were given conditional probabilities, so then we directly use these formulas. But do not directly use these formulas if you don't know the conditional probabilities or you can't figure it out. So that's going to be my big tip for you guys. Hope this video helps you a little bit to prepare. But I know probability rules do give people a lot of problems, so hopefully this video can help you.